Alright folks, it's time to try a couple of rate law practice problems. We've done 3 in your notes, and I would like you to take some time and try to do these without my help, and then of course come back to the video and see how you did. So for number 1, we have hydrogen gas reacting with acetylene, C2H2, to produce ethane. I have 3 different trials, and I vary the concentration of hydrogen and C2H2, and I have the rate of the reaction during those 3 different experiments. What I'd like you to do is find the order with respect to each reactant, find the rate law, solve for K, and let's go from there, okay? All right, let's see how you do. So pause the video and give number 1 a try, and then we'll see you in a second. Okay, welcome back. All right, so let's find the order with respect to H2 first, and then we'll do C2H2's order. Now we have to do that experimentally. We just can't look at the balanced equation and get it that way. We have to have experimental data. So it looks like in the first 2 experiments, do you agree that the C2H2 concentration did not change, but the hydrogen concentration doubled? What did the rate do? That's right, those are pretty numbers. Didn't it double? So we call that a direct relationship, and that means it's first order. Okay, so H2 is first order. What about C2H2? What experiments can we use for C2H2? Well, let's try to find where H2 is constant first. So let me get rid of this right here. Okay. And let's fill in that. All right. So it looks like from the first to the 3rd experiment, H2 is now constant. And the C2H2 doubled, didn't it? And what did the rate do? Yeah, the rate remained unchanged. So even though C2H2 concentration doubled, the rate didn't change at all, so we know that's 0 order. So C2H2 is a 0 order reactant. Well, now we can write the rate law. Remember, rate laws always start out with R equals K, and then we'll put our first reactant in there, H2, and we know that's to the first power, and the second reaction, C2H2, to the 0 power. We know it's a 0 order reactant. So then I asked you to solve for K. So K is equal to R over, it looks like the H2 concentration to the first power, and we can ignore the C2H2 because it's a 0 order reactant. So let's solve for K. We're going to use R from the first experiment, 1.5 times 10 to the negative 4th molarity units per minute. All right, and we'll divide it by the H2 concentration during the first experiment, 0.20 molarity units. So it looks like molarity units divide out, and our unit is 1 over minutes. So let's see what we end up with here. 1.5 second EE to the negative 4th divided by 0.2. So 1.5, let's plug that in again. Second EE to the negative 4th divided by 2 gives me a rate constant of 7.5 times 10 to the negative 5th, 1 over minutes. Alrighty. Pretty straightforward. Do you feel sort of kind of comfortable with that now? Alright, well, let's try another one then. Let's try this second one. So here we have nitrogen monoxide gas reacting with hydrogen gas to produce water vapor and nitrogen gas. I have 4 experiments for you. Let's add a 5th one here. Let's say the concentration of NO is 0.100 and the concentration of H2 is 0.200. Let's solve for the rate at the end, okay? And that would be the rate of N2 gas forming molarity units per second. So what you're going to have to do is find the order with respect to each reactant, find the rate law, solve for K, and then we can find this rate during experiment number 5. Okay? So pause the video, try it yourselves, then come back and see how you did. We'll see you in just a second. Alrighty, welcome back. So it looks like between the first and the second experiment, H2 stayed constant, didn't change, and N2, it was reduced in half. I don't like things getting smaller. It You can do it that way, but I prefer to go, okay, let's say we did the second experiment first. Okay, so we go from the second to the first, and that makes it look like it doubled, didn't it? And then we can see what happened to the rate. So let's see, 0.136 divided by 0.0339 is 4. So it four-tupled, quadrupled, and from the second to the first experiment when NO was doubled and H2 was held constant. So I know that NO is second order because I doubled it and the rate quadrupled. Okay? All right, now what about for H2? Which experiments did you use? So let's see, where is NO? Looks like NO is constant between the second and the third experiments, don't you agree? And it looks like H2 from the second to the third doubled. The rate from the second to the third, we don't even need a calculator for this, that also doubled. So it looks like H2 is first order. That's a direct relationship. So the order with respect to NO is second order. The order with respect to H2 is first order. If I asked you for the overall order, you would just add the two together and you'd say third. I didn't ask you for that, but if I did, that's what it would be. Now let's write the rate law. So rate laws begin with R equals K. So we have our NO reactant to the second power and H2 reactant to the first. And let's solve for K, which would be equal to R over the NO concentration squared and H2 concentration. And like we've always been saying, we're going to use the first experiment's data to solve for K. So the rate during the first experiment is 0.136 molarity units per second. The NO concentration is 0.420 molarity units, but we're going to square that, kiddos, because it's second order. And the H2 is 0.122 molarity units. So it looks like molarity units cancel out on one of those. We have 1 over second molarity units squared as our unit. And let's do the math. 0.136 divided by, now we're going to square the 0.420, so I'm going to use my parentheses key and put 0.42 caret key squared and close off the parentheses. And then I'm also going to divide by 0.122. And so it looks like I have 6.32 as my rate constant. So now that I have the rate constant, I can solve for the rate during experiment number 5. Remember that question mark that we had earlier? So what is the rate going to be? Well, R equals K, which is now 6.32, 1 over second molarity units squared, times the concentration of NO. So during that experiment, the NO concentration was 0.100 molar. 0.100 molar, and that's second order, kiddos, so we're going to square that. And then it's also times my H2 concentration, which is 0.200 molarity units. So it looks like those molarity units squared cancel out, and I have molarity units per second as my unit, which is perfect because that is a rate unit. So let's do the math and we'll see what we get. 6.32 times 0.1, and we're going to square that, kiddos, and times 0.2. And if you did it right, you get 0.0126 molarity units per second during that fifth experiment. We really don't have to do the experiment because we have our rate law and our rate constant. So we can then find the rate at any concentration of reactants. Okay? All right, I hope that helps. We're going to move on to something called equilibrium in our next chapter, so we'll look forward to that. See you soon. Bye-bye.